Welcome to part 2 of this series. In this video, we will go through the details of the computing square method, and based on that, we will derive and review the Vieta theorem. We will cover the applications using 8 examples. Hello, math champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the second session of the quadratic equation topic. The first question we are going to solve is a trinomial quadratic equation in its standard form with arbitrary constant a, b, and c. The only condition here is that the quadratic coefficient a is not allowed to be 0, because if a is equal to 0, it is no longer a quadratic equation. Instead, it becomes a linear equation. So the first step is to take out the quadratic coefficient a in order to make the quadratic coefficient as 1, and then based on the quadratic and linear terms here, a constant is added to make them a competing square. The required constant equals half the linear coefficient and then squared. After arranging the equation, we have a competing square on the left hand side of the equation, while the remaining constant terms are moved to the right hand side of the equation as shown on the screen. Since the left hand side is a competing square of x plus b over 2a, or in parentheses squared, it is always greater than or equal to 0. Due to the right hand side is equal to the result of b squared minus 4ac over 4a squared, so the condition for this quadratic equation to have real solution is that b squared minus 4ac must be greater than or equal to 0. By convention, b squared minus 4ac is defined as discriminant, and we use a simple delta to represent it. Based on the value of the delta, we discuss the possible outcome of this quadratic equation. The first criterion is that the discriminant is greater than 0. In this situation, there are two distinct solutions for this quadratic equation. The second criterion is that the discriminant is equal to 0. In this case, the quadratic equation has repeated roots. The last criterion is that the discriminant is less than 0. In this case, there is no solution in real number for this quadratic equation. In addition to the discussion, we also demonstrate here an alternative expression for the solution of this quadratic equation, given the condition that the discriminant is greater than or equal to 0. We start x1, x2 equals negative b plus minus square root delta over 2a. Then we multiply a conjugate of the numerator on both numerator and denominator, and then simplify them to get the final expression of 2c over the total of negative b minus plus square root of b squared minus 4ac. Question 2 is to solve a quadratic equation with a parameter m. Since one of the roots is 0, we need to use this information to find out the value of m, then to calculate the other root of this equation. To help you understand the way to solve this equation, we need to review the Vieta theorem first. As for a standard trinomial quadratic equation, if its discriminant delta is greater than or equal to 0, it has two solutions. One is the result of negative b plus square root delta over 2a, and the other is the result of negative b minus square root delta over 2a. Now, x1 plus x2 will result in negative b over a, while x1 times x2 gives the result of c over a. Since the question says one of the solutions is 0, so c over a must be 0. Therefore, the result of m squared minus 2 over the result of m minus square root 2 is equal to 0. So we calculate the value of m, which is a negative square root 2. After substituting the calculated m back to the original equation, the other root can be calculated, which is 3 square root 2 over 4. Example 3 shows a quadratic function with a parameter k, given the criterion that the range of this function stays positive. It asks us the value range of the parameter k. As we know, if the quadratic coefficient is positive, the graph is upright and has a minimum turning point. On the contrary, if the quadratic coefficient is negative, the graph is inverted and it has a maximum turning point. So in this example, in order to satisfy the criterion that y always stay in positive range, it must satisfy two conditions. The first one is that the coefficient of the quadratic term is greater than 0. The second one is its discriminant must be less than 0, which means that the graph is upright but not touch the x-axis. Based on that, two simultaneous inequalities are established as displayed on the screen. After factorizing the discriminant that expressed in trinomial quadratics in terms of k, we obtain the value range of k, which is between 2 and 8. Example 4 is to prove the quadratic equation has equal roots for all real values of k. The first step is to rearrange the quadratic equation to its standard form. Then we need to check the discriminant of this quadratic equation, because it is the parameter which determines whether or not a quadratic equation has real roots. So delta equals b squared minus 4ac, which is k squared minus 8k plus 16. This is exactly a complete square. K minus 4 all in parentheses squared, which is always greater than or equal to 0. So we have proved that this quadratic equation always has real solutions, no matter whatever the value of k it is. Question 5 has two sub-independent questions. The first one is to find the expression of k in terms of a and b, given the criterion that the equation has repeated roots. The second equation is to find the value range of p, given the criterion that the quadratic equation has real roots. For the first question, since the quadratic equation has repeated roots, its discriminant, delta, must be equal to 0. Therefore, we write down the expression of delta and then set it to 0. After simplifying the expression, we find the parameter k is equal to a squared over the result of b minus 2a. As for question b, since the quadratic equation has real roots, its discriminant, delta, must be greater than or equal to 0. So we write down the expression of delta in terms of p, which is 2p in parentheses squared minus 4 times the sum of p plus 1 times the sum of p plus 2. After cancelling the term of 4p squared, we get the result of p is less than or equal to negative 2 over 3. Question 6 is a question related to quadratic expression with the parameter k. It asks us to find the value range of k squared in order to enable the quadratic to be positive, and hence to find the value range of k. As required by the question, the quadratic expression is transformed to its turning point form by adding a constant term 6k over 2 or in parentheses squared, which is actually 9k squared. Please note, the quadratic coefficient is 1 in this case, so we can directly add a constant here. After simplifying, we have its turning point form of x plus 3k or in parentheses squared minus 9k squared plus 144. So in order to have the quadratics always stay in positive, q, which is equal to 144 minus 9k squared, must be greater than 0. Therefore, we obtain the value range of k squared, which is less than 16. Hence, we have the inequalities of k squared minus 16 less than 0, which gives the value range of k is between -4 and 4. Question 7 is a quadratic equation with parameters of p and q. It also tells us -2 and 4 are the two roots of this equation, and asks us to find the values of p and q. According to the Vieta theorem on these quadratics, we have p equals -2 plus 4, which result in p equals -2. Q is equal to -2 times 4, which gives -8. A quadratic equation is given in question 8, where x1 and x2 are the two roots of this equation. It asks us to calculate the values of various expressions of x1 and x2. Apart from directly solving this equation and getting x1 and x2, and then substituting into these expressions to get the results, initial inspection tells us Vieta's theorem can be used to provide all the answers for these questions. Let us apply Vieta's theorem here. However, you may solve this equation first and then use the roots x1 and x2 to calculate the results of these questions. As we remember, x1 plus x2 equals -b over a, while x1 times x2 equals c over a, as shown here. For the first and the second questions, Vieta's theorem can be applied straight away. So x1 plus x2 equals -5 over 2, and x1 times x2 equals -3 over 2. For question 3, since x1 squared plus x2 squared can be transformed to x1 plus x2 or in parentheses squared minus 2x1 x2. So the result of question 3 can be calculated, which is 37 over 4. For question 4, we need to recall the formula of the sum of two cubes, which is equal to x1 plus x2 or in parentheses times x1 squared minus x1 x2 plus x2 squared or in parentheses. Since we know from question 3, x1 squared plus x2 squared can be transformed to x1 plus x2 or in parentheses squared minus 2x1 x2. So the sum of two cubes can be expressed as x1 plus x2 or in parentheses times open square bracket x1 plus x2 or in parentheses squared minus 3x1 x2 close square bracket. Finally, we calculate the result of question 4, which is -215 over 8. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.